appropriately. um, thank you, and thank you for the audience for attending our series of webinars. Today, Bill Flynn and I will be your speakers for this webinar on buzzing boards, an example of dynamic testing, analysis, and modeling of a printed circuit board. Over the next 40 minutes, we'd like to talk about a specific case study that we have for testing modeling a printed circuit board where you have a buzzing component that creates acoustic noise. This has been an area of study and an area of application for our laser vibrometer, and we realized that beyond the testing aspect of this, there's also the aspect of modeling and validating your models that go along with this. So we kind of wanted to show a complete study together with Siemens where we show this as an example. So this is a little different from our previous webinars where we talk about specific applications. This is a very specific test case for an application in consumer electronics. So today's presentation, I'll talk a little bit about the background of what we want to show, noise and vibration of a printed circuit board, talk about the approach, the combined approach of testing and modeling together with Siemens. So Bill's going to be giving the second half of this presentation where he talks about the modeling and model validation aspect. I'm going to talk about laser vibrometry and how we do the test of vibration on this, and a little bit of background of why this test is important for electronics, for acoustics. Talk about our scanning vibrometer, and Bill will talk about the modeling, modal analysis, model validation, and some sound field simulations that he can actually do with the model. So a little bit of background about this, what's the process for doing this. So if you have a printed circuit board, a lot of times you start from the modeling aspect where you have a model of it and you want to validate that model. So we picked a case study where we have a lightweight component where it's important to test with the vibrometer, and you have a buzzing component on there that creates sound, it creates acoustic radiation. So how can we test that? How can we make a model on that? How can we validate that model? And what can we do with that model once we have it? So that's the goal of today's presentation. That's what we want to show with our combined presentation. So just to start with, on the testing side, I'll talk about that, and then Bill will take over and talk about the modeling and modeling validation side. Polytec, we make tools for vibration analysis. So we make tools for fast, accurate measurement and visualization of structural vibration. So this is used in quite a lot of fields. It's used on large structures like automotive or aerospace, where you want to scan and measure over a whole surface of an object. Use this for remote testing on outdoor structures, and in this case we use it for lightweight structures where you really don't want to attach an accelerometer because you could cause mass loading. So today's topic is going to be on printed circuit boards. Our technology is using laser Doppler vibrometry. This is a non-contact vibration measurement. Basically you're using laser light, and the laser has the property all the photons have the same wavelength, direction, and phase. We can split the light. One beam goes on the measurement object. The other one's a reference beam. The light that's backscattered from the vibrating object has a Doppler shift just from the vibration of the velocity of the object. We can measure that in real time and then give you a real-time velocity output from the measurement just using the Doppler principle, the formula you have in the lower right of the screen at the bottom here. So the advantage of that, besides being non-contact, you have real-time velocity and or displacement measurements. We have a broad frequency range from 0 hertz all the way up to 25 megahertz. We're using a laser spot, so we have really good spatial resolution. We can focus the laser beam down to less than 1 micron in size. Our resolution, our measurement resolution is down to picometer. So that's 10 to the 12 meters. It's very tiny vibrations. So we have no problem picking those up and measuring those. So it's a very sensitive tool. We'll see why it's important for this application today on acoustics on printed circuit boards. And we have a very high accuracy. Since we're using laser interferometry, inherently this is extremely accurate measurement. So today's topic is a topic within a topic. So talking about consumer electronics, and one of the biggest areas of measurement in consumer electronics is acoustics, trying to make quiet products. So anytime you have buzzing components, things that can vibrate, that could potentially create acoustic noise, enough acoustic noise where the user can hear it, and that's something you want to eliminate. You want to make quiet products. You don't want them buzzing, especially if it's something that has audio on it. Then you don't want it buzzing or creating unwanted noise, or it becomes unpleasant, or it actually interferes with other parts of the electronics. So that's one area of study. We also do a complete range of studies for electronics, audio, shock and vibration, modal testing, which we'll talk a little bit about today, other things that vibrate on electronics or cell phones, fan vibration, camera motors, haptics, inertial sensors, and an old one, not so important today, is disk drive. So today we're going to talk about acoustics. So a typical test for electronics, a lot of times we do shake tests. So the idea is that you want to measure the vibration of components on a circuit board. What we could do is, a starting point for that is to provide a shake test. If you want to do modal analysis, or you want to just see the response of an individual component on a circuit board to a shake environment, you can put on a shaker. You can run a specified shaker profile. So say if you want to run 5 Gs out to 2 kilohertz random vibration, you can run that on the shaker. You can measure how an individual component responds to that environment, and then look at the response and also the frequency analysis. So you can say, okay, how much did it respond at the resonant frequency? How much did it respond? You know, did it exceed 5 G at any point? Maybe that's a specification for a circuit board, especially if it goes on an automobile. And then you can see the relative movement of that part relative to the circuit board. So that's a typical shake test that we could do on a printed circuit board. The advantage is using the vibrometer. There's no mass loading. We're using a laser beam, so we're not attaching anything, especially on a lightweight board, that could be causing mass loading effects. We can resolve down to a picometer, so even the tiniest vibration we can measure, and then upwards if you're doing really high vibrations like shock, we could also measure those to high velocities up to 10 meters per second or even higher. So we can measure shock profiles. So we have a very high dynamic range. And I mentioned we're using a laser, so we have high spatial resolution. We can measure really small things, even down to the wire bonds or the individual wires on the wires coming from the components. So we also have a scanning vibrometer. So the scanning vibrometer has the capability of mapping out the vibration. So we can scan, map out, and display the vibration mapped over an area as a 3D animation. So we have this as a 1D scanning vibrometer that can map out a plane. This is commonly used for acoustics because we look at the outer plane vibration on a circuit board. That's what you want to look at for looking at vibration. We also have a 3D vibrometer, which can measure X, Y, and Z vibration. It's a little bit more sophisticated because it has 3 lasers, but the idea is perhaps for modeling, you might want to use a 3D vibrometer because you want to measure in all 3 directions, vibration in the X, Y, and Z directions. And I think Bill has an example on that also coming up that we did on a tube for 3D vibration. So how does the scanning vibrometer work? So with the scanning vibrometer, you of course have the laser vibrometer sensor measuring 1 point. We use scan mirrors to direct that to different points on the surface. We collect the vibration from those points, we store it, and then we scan sequentially point by point on the structure. So we capture all these vibration responses, store that, and then we're able to interpolate what the vibration shapes or the deflection shapes are in the structure. So we can save that data as time domain data or frequency domain. If you're looking at mode shapes, you want to look at the frequency domain, pick off the resonant frequencies, and then analyze that using modal software like we'll show today with Siemens software for doing that. So, so one requirement with this is it has to be a repeated excitation. With the scanning system, since we're measuring point by point, we have to have a repeated excitation. We can't be at every point simultaneously. Not with this system. We have a multi-point that can do that. But in this case, if you're running a shaker or some kind of excitation, you have to be able to repeat that excitation over and over again for each point that we measure. But then if you can repeat that. We can go up to 250,000 points, take all those points. And then what we're showing you here is an example of a turbine blade. You can see this is one of the modes on the structure. You can see that the vibration that's at a specific frequency, and you can see the blades that are vibrating at that specific frequency. So that's what you can do with the software, is come back and play those deflection shapes at any frequency on the spectrum. So for circuit boards, one typical test is modal testing. So if you have a circuit board, you have a layout of electrical components on there, you want to test that and extract modal parameters from this board. So by testing and then measuring over the whole structure and then mapping that out, you can do modal analysis. This leads to better design and changes at an early stage. So if you know exactly how your board responds, if there's an individual component that's causing unwanted vibration, you can identify that right away, make changes, test it again, and compare it. So a lot of times on circuit boards, if you have a processor and a heat sink, those are pretty heavy, and those can move quite a bit and cause bending and cracking for the wire bonds going to the processor. So this shows you what's happening. You do the modal analysis and you can optimize the design. So if there's something wrong with your design, you can actually change the layout of the components on the circuit board and then improve the design. So you don't have any unwanted resonances or any localized vibration that could cause problems like cracking or bending of the circuit board. So the test that we want to show today, we want to actually do a measurement on a circuit board, but we want to do it under operational excitation. So this is an example that we're showing right now. These are singing capacitors. So what we mean by that is, as we're powering up this board, this is a power amplifier board, the current going through these capacitors, the little elements that you see vibrating back and forth, that's enough to cause a sound output. So even though each one of those, they might be vibrating, you might not be able to hear the individual capacitors. At some level, having a series of these, the vibration gets amplified and it does become audible. So in this case, this was audible. Once you get above 5 or 10 dBs, then you can actually hear that. It becomes a buzzing sound, and that becomes a problem. So this is true with multi-layer ceramic capacitors. Once you push current through them, it creates a piezo effect that causes them to vibrate. That vibration at some level can become audible and become a buzzing sound that it's unwanted, and you want to troubleshoot and try and minimize or reduce. So this becomes an application where we have singing capacitors. So if you have an arrangement of these capacitors on a circuit board like we just showed, even though an individual one might not cause enough vibration to become audible, a series of these together on a circuit board can become audible. So the circuit board at certain frequencies or modes can amplify that sound and become more of a problem once you have these arranged on a circuit board. So the same is true for inductors. Inductors and capacitors have this piezoelectric effect where they vibrate and can cause this problem. This is affected by the individual devices, quality materials, how they're bonded and arranged on the circuit board, and just the 3D arrangement on the circuit board. So this is an area of study for acoustics. In general, anything acoustic, it sources back to the structural dynamics of the object. So sound is caused by vibrating objects. Even though you hear that sound, it's hard to know where that's coming from or what the transfer path is. So if you could trace that back to what's actually causing that, what part's actually vibrating, then you have a way of mitigating that or changing that, and then evaluating how that causes, what sound output that causes. So what we're looking at here is the transfer path, basically, for the vibration. The object vibrates, it has to couple to a medium. That medium transmits the sound, and then you hear it. So this is a chain of events that happen. We're attacking this at the structural level, the structural dynamics level, and then trying to solve the problem there. So typically on something like a printed circuit board, you want to measure the acoustic noise. So the first measurement might be a microphone where you power up the device. This would be like an example on a power amplifier. you take a microphone, you measure the sound pressure levels, and then you do an FFT of that measurement to look at the frequencies that are there. So this is an example. You have this in an anoic chamber. You can see you have padding around to kind of absorb any unwanted reflections of the sound. You're measuring directly at a point above the printed circuit board. And then what you're looking at is the FFT of the sound pressure level. So you're looking at resonances there. And if it's a buzzing component from it being powered up, here you have harmonics of 120 hertz all the way down the spectrum. And this creates a buzzing noise that can be undesirable, something you want to get rid of or at least reduce the effects of. So this is the problem. This is the general approach using microphones. What we want to show is a case study where we actually look at this from measuring the structural dynamics and then modeling it and then trying to predict what will happen and then evaluate, okay, if we change anything, how does that affect the sound output? So what we wanted to do together with Siemens is come up with a case study where we can actually take something that we can model, in this case, a very plain, flat printed circuit board, put a buzzing component on it, and then do the whole process all the way through, testing, modeling, validating the modeling, modal analysis, and then acoustic sound field prediction. So my end of it's pretty easy. We did the testing using the scanning vibrometer. So in this case, we just took a printed circuit board, a copper-clad circuit board. You can see all the dimensions here. This is basically an 8-inch by, or 9-inch by 6-inch circuit board, copper on the outside, and then basically printed circuit board material in the middle. What we did is created a model of this. So we actually created here a measurement grid of 1,426 points. This was actually based on the model, so I'm skipping ahead one step. Bill will explain the model next. But we imported the points from the model onto the circuit board, so we had the exact location of the measurement points from the model. We imported that and then superimposed that on the object as a measurement grid. And then we did measurements at every single point on all those measurement points on the grid, and then we overlaid that on the video. So, and then what we did to excite the structure is we tried to come up with a device that was a buzzing component. So the easiest thing that we can control would be a piezo transducer. We just attached it to one point on the circuit board at a known location. So I picked a point that was had the XY coordinates of 6.75 by 4.5 inches up in the upper right corner. And I picked that as the location, attached it there, and then that was our excitation source. So we vibrated the circuit board with that piezo element, and then we basically did a frequency sweep. So we put it in free condition. So if you can see it hanging there, basically it was in free condition, hanging. So the boundary conditions was basically just free to move. It wasn't really constrained. There were some constraints from the top from where we attached it by strings, but other than that, it was pretty free to move. And then we did a frequency sweep from 0 to 2.5 kilohertz in this case, and then look at the frequency response. So this is one technique that we've used for a number of applications, especially when you have small objects. We use a piezo transducer, and these are readily available. This is one from Thor Labs that you can buy commercially. The idea is it's a transducer. We just glued it right under the surface at the location I described. And then you're able to vibrate from that component. So by putting voltage through that, you have the piezoelectric effect. This vibrates that object, and that was our source of vibration. That's how we excited it. And what we tried to do was mimic a buzzing component. This is not really a buzzing component because it's the piezo, but the idea is we can control exactly how we excite that. We can set whatever waveform we want into that, excite the structure, and then measure it. So this was reasonably flat. So if this shows you the response of just the piezo. If you put the laser directly on the piezo transducer, it's not perfectly flat. You can see the piezo itself has resonances up in the 100 kilohertz range. But for our purposes, since we're only interested in acoustics, that's fine because the piezo itself doesn't resonate till higher frequencies. So this is up to 500 kilohertz. You can see if you do a frequency sweep from 0 to 500 kilohertz, the response, we'll call this more or less flat. It's not perfectly flat, but it's flat across the frequency spectrum. So we use an amplifier, so we can amplify this up to 200 volts into the piezo, so we can cause sufficiently high vibration levels. It's a capacitive load, so you have to be careful of that. In this case, we use 37.5 volts as an input to the piezo to drive it. And then what we did is we basically did a frequency sweep. So we swept from 0, in this case up to 10 kilohertz. Broadband excitation, we took measurements at every single point, and then we basically mapped that out. So each frequency in that spectrum, you can see the average FFT at the upper graph there. This shows you all the resonant frequencies going out to 10 kilohertz. And you can see several of those deflection shapes. I won't call them mode shapes because that's one of the next steps, but these approximate mode shapes. Our deflection shapes, which would be the response per how we were exciting the device, you can see those. So at 312 hertz, you can see this would be one of the bending modes of the structure. And as you go higher and higher frequency, you can see the deflection shapes all the way down the spectrum become more complex. And you get to a point out here where they become very complex and you would actually need more points to resolve those. But basically these are the modes. You have one more step to do with curve fitting and extracting the modes out of this response. So last slide I can show you before I give it to Bill. Basically, if you look at one of the frequencies, this is 700 kilohertz. You can see this is what the deflection shape looks like. We can show that in phase and magnitude and see what's happening at the board at that frequency. So any frequency in that spectrum, we can just put the cursor on it and then show you what that looks like as the deflection shapes. And this result given to you as a 3D animation, both phase and magnitude mapped over the structure. So that's our end of it. We did the test on the printed circuit board. The next steps will be for modeling and valid modal analysis. So I will hand that part of it over to my colleague, Bill Flynn. I will make him the presenter. And the presentation is yours, Bill.
Okay, thanks, Eric. Let's see, let me turn my screen on here. So can you see my screen okay?
Yeah. Yes.
Okay, good. Okay, so thanks, Eric, for the handoff here and allowing me to participate in this study. I think it was a really good study, and I think the tools that we show and the steps that we used in the process are very applicable to many different scenarios and even different industries for acoustic applications, but also for structural applications. And what I wanted to do first was to start off with giving an overview of kind of my area and Siemens area. We have this portfolio called Simcenter, and it entails 3 different components, main components of 1D system simulation, where we can simulate hydraulics, pneumatics, electromechanical. And then over in the lower right, we have another domain we called Simcenter 3D, and that actually includes the acoustic radiation prediction software that we have available. And this is an area, that you can use Nastran. This is where it's where you have mass and geometry, and we can model different structures through structural simulation. And then in the lower left, we have the domain that I come from, and that is in the test area. And the component of this that I'm going to show today, let me get my pointer up here. The part that I'm going to show today is involving our structures component of the test. So with our portfolio, we offer Testlab software and also SCADA's hardware. But for the customer, it depends on whatever is appropriate as far as what you use for acquisition. And so our study today, of course, uses the Polytec laser vibrometer. So what we also allow is some synergy between these 2 different worlds, and that is the correlation of a structural model through tests. So we want to validate the computer models, or what we call digital twin, and we validate these through testing. And we have structural correlation, and we can also do acoustic correlation too. With all of the tools that we present today, we also offer engineering services. So if a customer would like to get some training on the tools, or actually have us come out and do the tests for them, we can always do that too. So that's something that we also offer. So Eric presented this schematic here. This was kind of an overview of the process that we used, and these are the different components in the process. So first of all, we did some computer modeling of the flat plate of the PC board. We used Siemens Nastran NX for the modeling, and that was 1,426 C-quad 4 elements. And we found through analysis that there were 15 modes in the 50 to 800 hertz range. Then the next step in the process, we did pre-test analysis using FE model to optimize our modal test setup. Then did some testing with the scanning laser and then acoustic simulation. And this part right here was using directly the surface velocities that were measured. So with the laser vibrometer, that measures the surface velocities, and we can use that as direct input to acoustic simulation if we want to do it that way. Or else we can go down this way and send the data, the measured data with the scanning laser, to our modal analysis package and do some curve fitting. And with the modal analysis model, we can use that for correlation and feed that into a model correlation and model updating scenario. And then from that, using a correlated model, then we can use that for acoustic simulation. So that's the steps in the process that we used for this study. And I'll go into a little bit more detail, not too much, but a little bit more detail of each of those components. So like the pre-test analysis, what that is, and you see the schematic over here, we use the preliminary uncorrelated model, and we use that to set up a pre-test. And it's the best guess at that point where we can use that finite element model to help design a test setup. And then we can feed that into a test database and eventually produce results that we can do a correlation. So the objective of a pre-test is to optimize the test setup. And so in the case of accelerometers, or in, I guess, most cases, we want to minimize the number of points. And that becomes less of a point for laser scanning, because and it's less critical because we can very efficiently scan many points. With accelerometers, of course, you have to position those, and you've got cables and things, and the test setup goes up exponentially, and the complexity of the test setup. So and then also we use pre-test analysis in the computer model to find out where we want to excite the structure, and we find the optimal location for excitation. And that's an important step, even for simple structures like the one that we had for this study. And then also, of course, with pre-test, if you want to include the boundary conditions, you can do that as part of your modeling. The number of points that we wanted to use is kind of dictated by the acoustic requirements. So there's typically 6 points per wavelength, depending. So the wavelength depends on the frequency range that you want to cover, and that kind of tells you how many points that you need to measure. But with our computer model, as Eric said, we actually imported the nodal data from the FE model into Polytec and scanned at each one of the nodal points from the model. So with pre-test analysis, we use some correlation metrics, like we want to minimize the off-diagonal MAC terms, and I've got an example of that next. And then also, of course, we want to determine where to drive the structure. So this is the process in a pre-test. So you start off with your preliminary model and do some sensor selection, do a pre-test analysis, analyze the results of that through this MAC matrix. So this is a way to quantify the correlation between different modes. And of course, this will be an auto MAC. And so the modes that come out from a normal modes analysis, from FE analysis, you're going to produce a number of modes. And the idea is to be able to pick the points where you measure in order to distinguish one mode from another. And you do that through this, visualize this through this MAC matrix display. And then eventually, once you have reduced the off diagonal, you have a sufficient geometry to scan at or to measure at, then you would generate, in this case, we used a universal file, and we exported that into the Polytec database for scanning. So the next step in the process, so we did some testing, and again, we did the data transfer involved universal file throughout this whole process. So the data exchange was from finite element to Polytec, and then again, Polytec produced a universal file that could be picked up by Testlab. And so we had 41 finite element modes in the 50 to 24 hertz range. The study was that I'm going to show, and the results I show, is only up to 800 hertz. But we could also transfer the geometry. So you don't have to do it at the FE nodes, but that is an option, which is a nice option too. But you can just let the Polytec scanner scan in a certain area with a certain density of nodal information. And then the result of the test produced 1,425 FRFs. And in this case, since we weren't measuring the force, which is typically done in mobile testing, we just used the voltage signal to the exciter as the reference signal. So we measured velocity over volts, and those were the frequency response functions that we used for the modal processing. So a look at the stabilization diagram. So once you've got the data from Polytec and transferred up by the universal file into Testlab, then you can use those, the group of FRFs for the modal analysis. And this is a look at the stabilization diagram, which is an aid in pole selection. So the red trace here is the summation of all of the FRFs, 1,400 and so FRFs, and then the green trace is a mode indicator function, which are, again, these are just aids. The mode indicator function is looking at the real and imaginary relationships at resonance and using that information to indicate where modes may be. But also we can sum up all of the FRFs, and that's what the red trace is showing. We use a single reference in this case, and the example I have here, and this buzzboard was a really good example of when single reference modal analysis is not okay for closely spaced modes. And then operation deflection shape, if you got to be careful about that, because it's just a deflection shape, it's not a mode shape, and so you can't discern between two closely spaced modes, because you're just basically generating a deflection shape from the peaks of the FRFs. So in order to discern closely spaced modes, you need to use modal analysis. So again, this is the force was not measured. We measured velocity over volts, and so we don't have scale mode shapes because we're not measuring the forces, but that's okay. We can still use that information for our correlation studies. In this case, with a model order of 60, so in the parameter estimation, we used a model order of 60, and that produced 12 modes in the 50 to 800 hertz frequency range. And this is a look at some of the modes here. Let me see if I can get these to animate a little bit. got a stubborn one that won't animate down here in the lower right. But anyway, it gives you an idea of the first several mode shapes. So first mode shape is at 89.5 hertz. That's first torsion. And then mode 2 is it jumps up to 208 hertz. And you notice that there's a torsion mode 2. And then the next mode 3 is at 262, and that's a bending mode along this axis. And then the fourth mode is at 299.2 hertz. And for the savvy engineers out there, you'll probably recognize that there is a torsion mode, and then the next mode is a torsion mode. But what happened to our bending mode about this axis? And that kind of leads to the idea of the single reference case here that we had. And so in this case, we weren't able to discern between the first torsion mode and the first bending mode because we only had one exciter and a single reference case. So this is the next step is to do some correlation, and we can actually do some correlation within Testlab. And this is showing some results, and I'm going to open up Testlab here. And this is showing the MAC matrix. So it's actually a cross MAC between the simulation and test. So along this axis here, these are the FE modes, and then along this other axis are the test modes. So you can see the first mode, they correlate very nicely. There's a 98.5% correlation between those mode shapes. So that's very nicely correlated. And the frequency is a little bit off, by about 4 hertz. So the modeling was done really, really well. We can look at the next correlated modes, and those are correlated to 98% and slight difference in frequency. But notice that there was a mode missing here. So if I click on this cell right here, I can see there's that bending mode, which was picked up by the analysis, but we didn't pick that up from the test. And you can see right here is where the excitation point was. And so you can see that kind of aligns with the node line of that first bending mode. So it wasn't very well excited, and with the single degree of freedom curve fitter, we weren't able to pick up that first bending mode. So that illustrates the case of closely spaced modes, and you can see that this first torsion mode is at 89 hertz, and the first bending mode was at 88 hertz from the analysis. So 89 hertz versus 85, and then it jumps up to 88 hertz. So very close in frequency. Okay, let me switch back to the presentation mode and switch my displays and turn my pointer back on. Okay, so that's that. And another case that I wanted to present. So the case that we showed here with the printed circuit board, there's a lot of FRFs, and more than usual than probably any test that you would do with accelerometers, and that's a lot in itself. But we also did this test several years ago on this tube, and in this case it was using a scanning 3D laser. So in this case, we had to, of course, with the laser, you need line of sight. So we suspended this in free conditions, and we took 6 different acquisitions because we had to rotate it slightly and then do another acquisition and rotate it again and do another acquisition. And we did that 6 times. So we had 6 acquisition and data sets. Then in Testlab, what we could do was stitch all those data sets together, and then in the end we come up with a complete tube, which we used for our analysis. And that was in the bandwidth from 2 to 10 kilohertz. And these were extremely large files, so they were universal ASCII files, and there were 6 of these at 1 gigabyte a piece. So that's a lot of data to deal with, but it also shows that of course, Polytec is kind of used to those sizes of data sets, but also we could transfer that data through universal file and get it into Testlab. And that ended up with close to 6,000 measurement locations. And since we were measuring in 3D, that gave us X, Y, and Z measurement points with a 3D scanner. And that gave us approximately 18,000 frequency response functions. And so we were able to use that and do a complete analysis, and these are some of the results. We had mode 1 at 857 hertz and mode 2 at 1,295 hertz. So the next step, if you're going to pass the data, once you've done the modal analysis over here, you send that data into correlation into Simcenter 3D for the structural correlation using test results and the results from the Nastran NX model. And so we want to, in this case, we call this validating the digital twin. So the digital twin is the computer version of the real structure. We want to basically qualitatively, through just looking at the mode shapes, to quantitatively understand what kind of correlation that we have, and we can do that through the cross-MAC. And we also look at how close the frequencies are. And since we're measuring through modal analysis, we can calculate damping. We can also transfer that information to the finite element model in the correlation process. So the metrics that we use for the correlation is the modal assurance criteria and COMAC and modal scale factor, and also we can use the mass matrix for cross orthogonality correlation too. Then the next step after that, we want to update our model to align the results from the test and the simulation, and we do that through model updating. So with a model, there's some uncertainties in how it's modeled. With our printed circuit board, it's a pretty simple structure, and already the results are pretty well correlated. But sometimes, like there's some elements that aren't well understood, like in weld elements and connections between different components and things like that. So you're not too, as an analyst, you might not be too confident in how that has been modeled. So you want to take that information and depending on how the different components of the model, you want to do some sensitivity studies, like how sensitive a group of elements are, or take some design variables like the Young's modulus and mass density element properties, and you want to kind of characterize those as how confident you might be in those, and you can weight those and then also use those as input to the sensitivity analysis. So you can determine which of those properties of the model might be more sensitive to certain mode shapes of your target modes. And then using that information, you can do some model updating. So the next step that in the process that we used was for the acoustic predictions. And so first of all, the steps here, you've got a computer design and you have your CAD model, which then you can do some structural meshing and acoustic meshing, taking into account the boundary conditions and maybe some microphone points. You can do some acoustic radiation predictions. And so that's kind of the flow of how things work with the acoustic predictions. And sometimes maybe you might have some strong peaks of some resonant frequencies that might be getting excited, and you want to be able to analyze those and maybe to make some structural modifications to attenuate and mitigate some of those peaks in the acoustic response. So that's the flow of things. And in our case, we did the acoustic simulation, again, using direct surface velocity measurements, and that was input directly into the Simcenter 3D for the acoustic radiation predictions. But then after we did a correlation of the structure, we could take a correlated model, that printed circuit board, and we inserted it into an enclosure. And this could be for like a PC or whatever it might be. And you can then model the boundary conditions because you've got a correlated model of the printed circuit board. So then you could also add modeling of this enclosure and the boundary conditions of that enclosure, and use that in acoustic simulation prediction. So like you can see some holes in the enclosure here, and how the acoustic noise might radiate out through those holes. And so over here we've got kind of an enclosure of the structure, and we can predict sound pressures at different points around this acoustic mesh, and also then eventually calculate sound power from all the sound pressure measurements. And you can even, if you want to make some microphone measurements, maybe even do some acoustic correlation to see how your microphone measurements, how they correlate with your predicted results too. So that's what are the possibilities with the acoustic radiation prediction. And so in conclusion to the presentation today, Polytec and Siemens collaborated on this test, showing the measurements with a laser vibrometer of the buzzing board, and how those measurements could be used for not only the structural correlation and model updating, but also for acoustic simulation prediction. And we can do that with either the direct measurements or through updated finite element model or digital twin. So the results of the test using normal surface velocities can be used directly. So as I said, all of this can be applicable to many different scenarios and different industries even. And if anyone has any questions, I put our email addresses down here. So Eric's email here and my email here. And with that, I will turn it back over to Vikrant.